the uniform distribution. Why not? I have plenty of time and you can skip it if you're not interested. So the cycle time for trucks hauling concrete to a highway construction site is uniformly distributed. Now the uniform distribution, I don't know if you remember the few little times we talked about that. That one is an absolutely flat curve. It's straight across. And so these things are uniformly distributed over the interval from 50 to 70. So from that 50 to that 70. And that means that all this over here, which remember in a probability density function, this is the p of x. Remember our binomials, probability of x's go down here, and our random variables go down here. So this is in minutes for this uniform one. So if we know that this thing has to have an area under the curve of 1, because every probability distribution function's probability must sum to 1, then what we have to do is find out how far this interval is. So 70 minus 50 says that that interval width is equal to 20. And so if that's equal to 20, then we have to find out what this height is in order to give an area of 1. So the area under the curve, right, that must equal to some probability times 20 such that we're going to get 1. So in other words, that probability is equal to 1 divided by 20. So this height right here is 1/20th. So that is the probability that we have here. Now, the next thing that we want to do is we want to find the average amount of time that it takes for the cycle. Well, the average amount is the mean amount. So what we're looking for is the balancing point in here. Well, the balancing point in a big rectangle would just be the midpoint of this. So that would be 70 plus 50 and then divided by 2, because that's how you find the midpoint of a line. So that would be 120 divided by 2, which would be 60. And so that would be the average. The average here is 60 minutes. So the mean amount of time that it takes is equal to 60. So the next thing that it takes, the next thing that we're asked here is what is the probability that it will take the truck more than 55 minutes. So 55 minutes would be over here, so let's go ahead and put that in. And if this is 60, then I'll call this 55, right? And so if I want to know that probability, then what I'm being asked to find is the area under the curve right here. So the probability that x is greater than 55 is equal to the width of this interval. 70 minus 55 is the width of that interval, and then times the probability, because it's just finding the area under the curve. So the area is the width times the height, length times the width. And so 15 is our, 15 is our width here, and then times 1/20th. So we have 5 going into both 15 and 20, so that's going to give us 3/4, or 0.75. So our probability here would be 0.75. Now our next question says, what is the probability that it will take the truck at most 65? So at most 65, now we're saying up here, and that is the most that it will take us. So we would be looking for this area down here. Well, these two are actually pretty much the same areas, right? So 50 to 65 is another 15. So we can say that the probability that x is less than 65, or less than or equal to 65, is again 3/4, for the exact same reason that probability of being more than 55 was 3/4, or 0.75. All right, moving on to the next problem. What is the probability that it will take longer than 65 minutes if you know it's taken longer than 55 minutes? Well, this is a conditional probability, right? So if we have this problem here, if we know it's already, or what's the probability that it's going to be, longer than 65, and we're given that it has been longer than 55 minutes. This we know from definition in Chapter 4 is the probability that x is greater than 65 and x is greater than 55, and then that's divided by the probability of the condition x being greater than 55. So this is just a little bit of a interval here that we would take into account. So if we said, okay, here's 55, right? And here's 60, and here's 65, and we just do a little bit of graphing. So x is greater than 55, that starts here and goes up this way, right? And then if I change the color and I say, okay, well now I'm going to do purple, and this one, now this one's 65 here, and I want to know where these two overlap, because that's what the and means, right? Where they overlap. Well, they overlap in this area right here from 65. So really what this ends up being is just being x is greater than 65. So we have the probability that x is greater than 65, and you're going to have to ignore the black in between here. So let me erase this one out so you can see my probabilities here. So my probability being greater than 65, well, that's 5 in there, right? So that's 5/20ths, and 5/20ths is 1 over 4, and then that's times well, actually it's divided by, and it's divided by the probability of being greater than 55, which is 3/4. And when we divide fractions, we multiply the first fraction by the reciprocal of the second fraction, and so the 4's cancel out, and that probability is 1/3. So that would be the probability that it's going to be more than 65 minutes, given that we already know we've waited for 55 minutes. And this idea here, again, is just to solidify really the idea of the area under the curve being equivalent to probabilities. And we can see that we can actually find that with these